In our last video, we focused on the composition of functions. In this video, we'll focus on inverses of functions. So graphically speaking, if we have a function f of x equals 2x minus 1/5, represented by this line. I'll make it pink so you can refer to the pink line. If you can imagine an invisible line, y equals x, I'll draw it in. That would have a y-intercept of 0 and a slope of 1. You see this invisible line? I want you to imagine reflecting that pink line over the blue line. In other words, pretend you could pick up this graph and fold it on this blue dotted line. Where would the red ink touch? Well, this part of the red ink, or the pink ink, would be over here, and this part of the pink ink would be down here. So graphically, that's how we find an inverse. We reflect it over the line y equals x. And I know how much you guys really enjoy your geometry, so it's kind of a nice nod to go back to geometry, what that means. Every point on the pink line is the same distance to the blue dotted line as the green line points, respectively. But how do we find this algebraically? What if we don't have a graph available? Well, we're going to replace f of x with y in the original equation. Then we're going to switch x and y and solve for y. It's that simple, these 3 steps. Let's take an example and practice doing just that. So the first step, we want to replace f of x with y. And next, we want to switch x and y. So my next line will be x equals 2/3 y minus 1. And then finally, we solve for y. So to solve for y, I need to add 1 to both sides. X plus 1 equals 2/3 y. Again, I'm trying to solve for y. I want to get y by itself. So the last thing I need to do is multiply by 3/2 on both sides, because that will eliminate the 2/3. So now we have 3/2 x plus 3/2, I get that by distributing on the left side, equals y. And the last step that's not really officially listed there is to replace this y with f inverse of x. That's just function notation for inverse. So what does this look like when I graph them? So I'm going to graph my original equation here, y equals 2/3 x minus 1. That means begin at b, -1, rise 2, run 3. And that's how I get my first line. This is f of x right here. Get it right through my graph. So this is f of x. Next, I'm going to graph f inverse. F inverse of x is right here. That says begin at 3/2, which is 1.5, and go up 3 over 2, or down 1, 2, 3, back 2. So when I connect these points, hopefully there'll be a reflection about the line y equals x. That invisible dotted line that would run right through our coordinate grid. Let's get this green line looking nice. Okay, there we have it. So the green line is my inverse, f inverse of x. And sure enough, if I draw that invisible line, y equals x, right through my graph, they are symmetric about that line. Let's try another one. Let's try this second one. I'm going to replace f of x with y. Then I'm going to switch x and y. So now I have x equals 2y minus 3. I need to get y by itself by adding 3 to both sides. And dividing by 2, which means y equals x over 2 plus 3 halves. Again, I would change this to f inverse of x for my final line. So if I want to graph these, the first one says begin at -3, and my slope is 2. So I'm looking to put a line on my graph right through these points. Next, I'll graph my inverse. I'm going to begin at 3 halves, which is 1 1/2, and I'm going to go up 1, right 2. Down 1, from 1 1/2 down 1 is 1/2, back 2. And I'll connect them. Sometimes we want to know if two functions are inverses, so one way to determine that, again, is to graph them. However, if you do not have graph paper available, access to graphing technology, another way that you can verify if two functions are inverses is to use composition, which we did in our last video. For example, if we want to determine if f of x and g of x are inverses of one another, we want to compose f of g of x and g of f of x. If both of those equal x, then these two functions are inverses of one another. If we were to graph them, they would be reflections over the line y equals x. So let's start with f of g of x, which again just means f of g of x. That means to start with the f function, because that's the first letter here, 2x minus 7. And I'm going to take out x, put parentheses so I know where it was right there, and I'm going to put g inside, 1/2 x plus 7. All right, now we simplify. 2 times 1/2 cancels out, and I'm left with x plus 7 minus 7, which equals x. So this one worked. Let's go next and try to figure out g of f of x, which is just g of f of x. Now I'm going to start with the g function, 1/2 x plus 7. Going to erase x, and I'm going to put in what x equals. In this case, x equals f of x. So 2x minus 7. Okay, now we're ready to simplify. I'm going to work inside the parentheses first. So 1/2, 2x minus 7 plus 7, those are like terms and they cancel. Half of 2x, the 2's cancel, and I'm left with x. Therefore, these two functions are inverses of one another. Let's scroll down to this example 3 in our notes and test this one. We want to find f of g of x. So I'm going to start with my f function, 1/2 x minus 10. I'm going to take out x, and I'm going to put g of x inside of it, 2x plus 1/10, and simplify. If I multiply by a 1/2, I now have x plus 1/20 minus 10. Since I don't have a calculator handy, 10 would be 220ths. So I have a common denominator, which would give me x minus 199 over 20, which does not equal x. So right away, I don't need to compute g of f of x. I can just stop right here and say that these are not inverses. Because f of g of x does not equal x. Remember, they both have to equal x. So if it did equal x, we would still have to check g of f of x. But since it doesn't, we are finished.